Anya, and today on Math and Science Concepts, I'm talking about Newton's third law. But before we begin, make sure to like, share, and subscribe, and hit that notifications bell so that you never miss another one of my informative videos. So let's begin. To every action, there is an equal and opposite reaction, said Isaac Newton. With our previous presentations in the series, we have considered force as a push or pull. However, if you think about it, you realize that no push or pull ever occurs by itself. When you push on a wall, the wall pushes back on you. And this brings us to Newton's third law. The third law states that for every action in nature, there is an equal and opposite reaction. If object A exerts a force on object B also exerts an equal and opposite force on object A. In other words, forces result from interactions. Newton's third law describes the fundamental nature of forces, which always comes in pairs. These paired forces are known as action-reaction force pairs. The law states that whenever a force is applied, another force of equal magnitude but in the opposite direction is simultaneously applied. These forces act on different objects, which is why they do not cancel each other out. Forces in the universe do not act alone. Every force has a partner force. This pairing is crucial to the understanding of interactions between objects, from the microscopic to the macroscopic scale. Force pairs consist of the action force, which is the initial force applied by one object, object A, and the reaction force, which is the force exerted in response by the other object, object B. These forces are equal in magnitude but in opposite directions, and they act on separate objects, so they do not cancel out. Newton's third law, for every action there is an equal and opposite reaction, is relevant to a pendulum's motion, particularly when considering collisions or interactions with other objects, such as in a Newton's cradle, where the energy transfer between pendulums demonstrates this law. Restoring force. When a pendulum bobs is displaced from its equilibrium position, a restoring force due to gravity acts on it, pulling it back towards the center. Tension. The string or wire supporting the pendulum exerts a tension force on the bob, which is the reaction force to the bob's weight and gravity. Collisions. In a Newton's cradle, when one pendulum bob collides with the next, the force exerted by the first bob is met with an equal and opposite force from the second bob, causing the transfer of energy and motion to the other end of the cradle. Some of the examples we see in the pendulum motion are swinging. As the pendulum swings, the tension in the string and the restoring force due to gravity are constantly acting on the bob, resulting in the oscillatory motion. And stopping. When the pendulum stops swinging, the forces acting on the bob, gravity and tension are balanced, and the pendulum is at rest. Newton's third law of motion states that for every action there is an equal and opposite reaction. This means that if an object A exerts a force on object B, then object B will exert a force of equal magnitude but in the opposite direction on object A. These forces are always equal in size and opposite in direction, and they act on two different objects. The mathematical expression. If object A exerts a force FAB on object B, then object B exerts a force FBA on object A. Mathematically, this can be written as FAB equals negative FBA, where FAB is the force exerted by object A on object B, and FBA is the force exerted by object B on object A. And the negative sign indicates that the forces are in opposite directions. Some common misconceptions are action-reaction pair misunderstanding. That is, a common misconception is that the action and reaction forces cancel each other out. However, this is not the case because they act on completely different objects. Therefore, they do not cancel out, but instead result in a change of motion. Equal and opposite forces. It is important to note that while the forces are equal and opposite, the effects of these forces might not be the same. The acceleration of each object depends on its mass, as per Newton's second law, that is F equals ma. So now, moving on, according to the law of actions and reactions, when two bodies are engaged, they apply forces to each other that are equal in magnitude and opposite in direction. This law is useful in studying the motion of objects that are in a static equilibrium or the objects that are in linear motion. This can be explained by the example as a book resting on a table exerts a force on the table and the table exerts a normal force on the book. The action force by the book and the reaction force by the table are equal. Mathematically, the law of actions and reactions is shown in the image on the slide. Here, F12 is the force applied by body 1 on body 2, and F21 is the force applied by body 2 on body 1. The minus sign indicates that the two forces are applied in mutually opposite directions. Forces always occur in pairs. If two bodies A and B exist within a system, then the force of A on B and force B on A become internal forces of the system, and they cancel each other out since they are opposite in direction and equal. As a result, the system maintains its equilibrium. But do not mistake this. The forces do not cancel each other out, as in the F12 still acts on object 2 and F21 acts on object 1. Let's take a look at one common application of the Newton's third law. A classic example of Newton's third law in action is a book resting on a table. The book exerts a downward force on the table due to gravity, the action force, and the table exerts an upward force on the book, the reaction force. These forces are equal and opposite, preventing the book from falling through the table. The explanation. Action. The book pushes down on the table due to its weight and the gravitational force. And the reaction force. The table, in turn, pushes up on the book with an equal and opposite force known as the normal force. Equilibrium. These forces balance each other out, resulting in the book remaining at rest on the table. If the table couldn't exert an equal and opposite force, then the book would accelerate downwards and fall through the table due to gravity. Newton's third law, often stated as, for every action there is an equal and opposite reaction, is a fundamental principle in physics that governs interactions between objects. Here's an easy way to remember Newton's three laws of motion. The first law. One day Newton was walking by a field when he saw a cow grazing. He kicked the cow, and because it hurt her, because of inertia, she walked a few meters. With this, he concluded, a thing will not change its state of motion or rest unless an external force acts on it. Thus, the first law, known as the law of inertia. The second law. Newton kicked the cow again, and the cow screamed, "Ma!" With this, he concluded the second law. A force applied is equal to mass times acceleration, or F equals ma. And the third law. Newton kicked the cow for a third and final time. But this time, the cow kicked Newton back with an equal and opposite force, and then kicked them with the other leg to remind you that in every interaction, forces are found in pairs. With this, he concluded, for every action, there is an equal and opposite reaction. In every interaction, forces are found in pairs. Note, Newton didn't really kick cows, but this is a really great mnemonic for remembering his laws. And here's a quick recap slide. Please go through it, and with that, we come to the end of Newton's laws. Until next time, ciao!